So hello everyone, welcome to the channel. So in this video I'm going to show you a multi-year coastline extraction and change detection using Landsat 8 imagery in Google Earth Engine. So now let's get started. So the study aims to assess and monitor the spatial dynamics of the coastal boundaries over a decade by utilizing the freely available satellite dataset. And so the coastline change detection plays a vital role in understanding the coastal erosion, accretion, and the overall geomorphological evolution of shoreline environment, influenced by both natural and anthropogenic activities. So the study area delineated as a polygon along the southeastern coastal regions of India. So the Landsat 8 surface reflectance imagery from 2014 and 2024 was selected to generate an annual composite representing the coastal condition in each year. And further, a pre-processing workflow includes cloud and shadow masking using the quality assessment band and radiometric conversion of optical and thermal band to obtain atmospherically corrected reflectance value. So this process ensures that only high quality pixels are retained, thereby minimizing the influence of haze, cloud cover, atmospheric distortions. The selected spectral bands like blue, green, red, and near infrared, short wave infrared, and short wave infrared 2 were combined to form a median composite that accurately captures the land and water features of the coastal environment. So, further, to extract the water body and delineate the coastline boundary, a automated water extraction index was applied, which enhances the contrast between the land and water feature using a combination of green, NIR, and shortwave infrared band. So these the automated water extraction index image was further refined using the Otsu Thresholding technique, which automatically determines an optimum threshold to separate the water from known water areas, producing a precise the water mask for the both 2014 and 2024. So the resulting binary water masks were then vectorized to derive the coastline boundary, which was simplified to create a clean and continuous shoreline feature. So for change detection, the two coastline datasets were compared through the bandwise difference analysis, so highlighting the areas of coastal erosion and accretion between the 2014 and 2024. A positive and the negative values in the difference image represents a seaward and landward shift in the coastline, respectively. So the visualization employs a color palette where the blue tone indicates the water gain, that is accretion, and the red tone signifies the water loss, which signifies the erosion. Finally, the extracted coastline vector for each year were exported as a shapefile to Google Drive for further spatial analysis or cartographic representation. So this automated workflow demonstrates the capability of our Earth Engine to perform a large-scale and multi-temporal coastal monitoring effectively using cloud-based computations. So the approach not only reduces the manual processing time but also ensures the reproducibility and scalability for a continuous shoreline assessment. So now let me get back to Earth Engine. So our aim of our study is to extract the multi-year coastline and perform the change detection using Landsat 8 imagery in Google Earth Engine. So let's get started. So first step, we're going to define a region of interest. So to define a region of interest, you can able to see here we have defined a variable here. So to create a region of interest, first I'm going to navigate to this option called draw a rectangle. So once you have navigated to the option called draw a rectangle here, so choose your suitable study region of your choice here. For example, I'm going to select this set of coastline along the Chennai coastline as a region of my interest. To select this particular as my study region, I'm going to navigate and click this option called draw a rectangle. And once you click that, in the next step, we're going to draw a rectangle over our region of interest. So for example, I have drawn my region of interest here. And in the next step, I'm going to click this option called exceed, and I'm going to turn this off. And in the top section, we have this new variable called geometry has appeared here. And I'm going to click this option called show generated code. So in the show generated code, we have the set of latitude and longitude here, so we can able to see that. So we're going to copy this latitude and longitude of a newly created study region. I'm going to copy using Ctrl C in my keyboard. So Ctrl C to copy, and once you copy it, we're going to paste it inside this variable here called study area. So I'm going to paste it inside this variable using Ctrl V. So now I have pasted. So in the next step, once we have pasted it, we have defined this variable study area is equals to earth engine dot geometry dot polygon. So we are specifically using this set of code in order to convert this latitude and longitude into a polygon. So for that we are defining this particular dot, that is earth engine dot geometry dot polygon. So once we defined a region of interest, the next step I'm going to center this particular layer using map.center object study area with a suitable zoom level of a choice. For example, I'm going to mention this 5 as my suitable zoom level. So in the next step, I'm going to add this layer. So to add this layer, I'm going to mention map.add layer, study area, and the color I'm going to mention as the visualization parameter as yellow, and we're going to output the layer as study area. So once you did that, in the next step, I'm going to click this option called run, and now let us visualize a region of interest. So let me increase the zoom level here. I'm going to increase up to 10 here, and I'm going to run this, and it's much better now. So we're going to navigate to the layer section, and I'm going to turn on the study area here. So this is our region of interest. You can able to see this part is the yellow color, which indicates our region of interest. So in the next step, we're going to define a function to prepare our Landsat composite imagery. So to do that, to create a new function, we're going to navigate this option, and we're going to mention this function here. I'm going to mention is get Landsat composite, and the start date, which going to mention the start date of our analysis, the starting time period of our analysis, and the end, which states the end period of our analysis. So we have to mention the date here. I'm going to mention it in the next steps here. So in the next step, I'm going to load my Landsat 8 surface reflectance imagery. So to do that, I'm going to mention a variable L8 is equals to earth engine dot image collection Landsat LC08 collection to tire top of the atmosphere. So collection to T1L2, that is surface reflectance data. So this is a surface reflectance data set. So that is T1L2. So in the next step, we're going to filter it based on our suitable timeline. So for example, I'm going to mention the function called dot filter date, start date, and end date. And the next step, I'm going to mention the based. I'm going to clip it based on our region of interest. So to filter based on our region of interest, I'm going to mention dot filter bound study area. So study area, which represents this is our study region. So you can able to see this is our study region. So in the next step, we're going to create another function to mask clouds and cloud shadow using QA pixel band in our Landsat 8 imagery. So let me show you this particular imagery. So this is USGS Landsat 8 level 2 collection 2 tier 1. So the dataset availability is from 2013 to 2025, and the dataset provider is USGS. And using this particular code, you can access the Landsat 8 imagery. So this short description about this dataset. So this dataset contains an atmospherically corrected surface reflectance and land surface temperature derived from the data produced by Landsat 8 AWEI TIRS sensor. These images contains 5 visible and near infrared bands and 2 shortwave infrared bands processed to orthorectified surface reflectance, and one thermal infrared band processed to orthorectified surface temperature. So they also contains an intermediate band used in the calculation of ST products, that is the surface temperature, as well as the QA band. So now let me navigate to the band section here. So in the band section, you can able to see we have set up for the bands that is available, starting with SRB1, that is ultra blue coastal aerosol surface reflectance, and SRB2, that is B2, that is blue band, and SRB3 is green band, and SRB4 is red band, and followed by SRB5 is near infrared, SRB6 and B7 are shortwave infrared band. And last is we have a set of bands, the ST, which represents the surface temperature band here. And last we have the QA pixel band. So this is a pixel quality attribute generated from CF mask algorithm. So this is a QA pixel band here. And let me get back to Earth Engine. So by using this QA pixel band, we're going to mask out the cloud and cloud shadow in the imagery. So to do that, we're going to define a variable. We're going to select the quality assessment band for in the first step. So we're going to mention this variable. So make sure that before we mention the function here, so for that I'm going to mention the variable mask cloud is equals to function img, and next step we're going to select the quality assessment band. So for that we're going to mention the variable QA, that is quality assessment, equals to image dot select. So we're going to select this particular band called QA pixel band. So you can able to see we have this QA pixel band that is available in Landsat 8 Imagery. So in the next step, we're going to create a mask where both the cloud and cloud shadow bits are 0. So to do that, we're going to mention variable cloud shadow is equals to the QA dot bitwise, and 1 is smaller than 3 dot equals to 0. And similarly for variable clouds, we're going to mention the variable clouds equals to QA dot bitwise, and 1 is smaller than 5 and is equals to 0. And last, we're going to mention another variable called variable mask is equals to cloud shadow dot and clouds. And in the last step, it's going to mask out those cloud shadows and shadows in the cloud shadows and the clouds in the satellite imagery. So in the next, we're going to define another variable called optical is equals to img dot select srb dot star. So it's going to select all the surface reflectance band of optical bands here. For example, these are the set of optical bands here. So you can able to see these are the optical bands, and we're going to select all those using srb dot star, and we're going to mention dot multiply. We're going to mention so we're going to apply the scaling factor to our Landsat 8 imagery. So to do that, to apply scaling factor, we're going to mention dot multiply 0.0000275 and dot add the offset factor, that is dot add minus 0.2. And similarly, to apply the scaling factor for the thermal bands here, so first we're going to define a variable thermal is equals to img dot select st band, surface temperature band dot select all. So it's going to select all the thermal bands. So we have only one thermal bands here. So to apply the scaling factor, we're going to mention dot multiply 0.00341802 dot we're going to add the offset factor, that using dot add 149. So you can able to see here we have the scaling and offset factor. So these are the optical bands. So which has a similar scaling and offset factor, scaling of 2.75 into 10 power minus 5 and offset factor of minus 0.2. And similarly, the surface temperature band has a scaling and offset factor. So it has a scaling factor of 0.00341802 and the offset factor of 149. So this is the scaling and offset factor for the ST B10 band. So in the next step, we're going to apply the mask to the image. So to apply the masking to the image, we're going to mention the return image dot add bands optical, and similarly dot add bands thermal, and last we're going to mention dot update mask, so representing this particular variable. So we're going to represent this particular variable called mask, so where it's going to mask out the cloud shadow and the shadows in the satellite imagery. So in the next step, we apply the mask and take the median. In the next step, to apply the mask and take median, we're going to mention the variable called composite is equals to light dot map. So we're going to apply this masking function. So we're going to mention dot map mask cloud. So it's going to apply this masking function to the Landsat 8 imagery. So next, we're going to select dot select the following bands: the SRB2, SRB3, and SRB4, SRB5, SRB6, and SRB7, blue, green, red, the near infrared, short wave infrared 1, and short wave infrared 2. So the SRB2 represents blue, and SRB3 represents green, and SRB4 which represents red, and SRB5 which represents the short wave infrared. There is a near infrared, and the SRB6 which represents the short wave infrared 1, and SRB7 which represents the short wave infrared 2. So to acquire a median imagery, so we're going to mention the statistical function called dot median function. So it's going to give us a median median imagery. And last, we're going to clip it based on a region of interest using dot clip function study area. So study area is this particular boundary we created earlier. So in the next step, last, we're going to return the composite. So once we did that, next step, we're going to generate the composite for 2014 and 2024. So basically our analysis involves extracting the coastline for the year 2014 and 2024. So to generate the composite for 2014 and 2024, so we're going to mention the variable called img 2014 is equals to get Landsat composite So we're going to mention the time period, that is the start period and the end period. So the start period we're going to mention 2014 January 1 and the end period, so we're going to mention the 2014 December 31st. Similarly, to mention the second imagery, that is for 2024, we're going to mention the variable img 2024 equals to get Landsat composite 2024 January 1 to 2024 December 31st. And last, so to visualize in our RGB composite, we're going to mention the variable RGB style is equals to. So this is the visualization parameter. So to visualize in the RGB composite, we're going to mention this visualization parameter, that is variable. So the RGB style is equals to bands. So we have red, green and blue. So it's going to represent a true color composite, and with a minimum of 0 and a maximum of around 0.3. And last, we're going to add this layer. So to add our 2014 and 2024 imagery, so we're going to mention map.add layer image 2014 RGB style. We're going to output the layer name as Landsat composite 2014. And last, to add the layer for 2024, we're going to mention map.add layer image 2014 2024 RGB style, which is the visualization parameter representing this particular variable, and we're going to output the layer name as Landsat composite 2024. And the next step, we're going to define the water extraction using automated water extraction index. So to define the water extraction using this particular index called automated water extraction index and Otsu. So we're going to use both the combination of this to extract the water, the coastline of the study region. So to do that, first we're going to mention the function called extract water image. And the next step, this is the formula to calculate the automated water extraction index. So this is the formula. So AWEI is equals to 4 multiplying green minus short wave infrared 1 minus 0.25 multiplying NIR plus 2.75 multiplying short wave infrared 2. So this is the formula to calculate the automated water extraction index. So in the next step, I'm going to mention another variable called AWEI is equals to image.expression. So in the expression, we're going to mention the formula. So the formula is 4 multiplying green minus of short wave infrared 1 minus 0.25 multiplying the near infrared plus 2.75 multiplying the short wave infrared 2. So the green which represents the image dot select green. So that is we have defined here. So you can able to see here the green which represents the SRB3, and the red represents SRB4, and the NIR which represents the SRB5. So here we are mentioning the green as image dot select green, and NIR we're going to mention image dot select NIR, and the short wave infrared 1 we're going to mention the image dot select short wave infrared 1, and last is the short wave infrared 2 we're going to mention as image dot select short wave infrared 2. And last we're going to rename as automated water extraction index using dot rename AWEI. So this particular index is very useful in case of water pixel will yield a high positive AWEI value, and the non-water pixels like the land, vegetation, shadow will yield low or the negative AWEI values. So this indices will enhance the spectral separatability between the water and land. So in the next step, we're going to apply the Otsu threshold. So normally the Otsu method calculates a threshold that minimizes the variance within the 2 pixel group, water and non-water. So the next step, we're going to define this variable called threshold is equals to automated water extraction index dot reduced region, and inside this I'm going to mention the reducer is earth engine dot reducer dot percentile 50. So the approximation to the median threshold, and the geometry is our study region, and the spatial resolution is 30 meters. And last, to get the value in the list, we're going to mention dot value function, and to get the first value of the list, we're going to mention dot get 0. So in the next step, we're going to define another variable called water mask is equals to the automated water extraction index dot greater than the earth engine dot number threshold, so which represents this particular variable, and dot rename as a water mask, and we're going to return water mask. So in the next step, we're going to extract the water for both the years. So to do that, we're going to mention variable water 2014 is equals to extract water img 2014. So this is a function here, so you can be able to see that. Let me show you that. So this is a function we have created earlier, and similarly I'm going to define another variable called water 24 is equals to extract water img 2024. And last, to add this layer, we're going to mention map.add layer water 2014 minimum of 0 and a maximum 1, and color palette start with the white and blue, and we're going to output as water mask 2014. And similarly, to add another layer, map.add layer water 2024 minimum of 0, maximum 1, color palettes white and cyan, and we're going to output the layer as water mask 2024. Run this code and visualize the result here. So I'm going to run this code, and we're going to navigate to the layer section. And first, let us turn on this layer called Landsat Composite 2014 here. So I can able to see this is our Landsat 2014 composite image, and this is our Landsat composite 2024. So you can able to see both the image here, and we can navigate to this option, and the custom section I'm going to mention stretch 90%, and I'm going to click apply, and now you can able to see the Landsat composite 2014. Similarly, I'm going to click this Landsat composite 2024. I'm going to click this option, and the custom section I'm going to mention stretch 90%, and I'm going to click apply. So now here you can able to see the results here. This is the Landsat 8 of 2024. So in the next step, I'm going to turn on the water mask of 2014 and water mask of 2024. Let us visualize the result. So it's loading the data. So now here you can clearly able to visualize this. This is our water mask of 2014 here. So you can able to see the distinction between the land versus the water pixels. So you can able to see the difference here, the land versus the water pixel versus the land pixels. The land pixels are highlighted in white, and the water pixels are highlighted in blue color. You can able to see. So in the next, I'm going to turn on water mask of 24. Similarly, similar to that image, you can able to see the difference between the land versus water. And using this difference, we're going to extract the coastline here. So let us navigate to the next step here. So in the next step, we're going to vectorize the coastline boundary. So now we're going to vectorize the coastline boundary. So we're going to create a function called vectorize coastline. So we're going to mention the water image, and the unit is in year. And the next, inside the function, I'm going to create another variable called coastline is equals to. So water image dot self mask function. So we're going to mention self mask function, and dot produce to vectors. So it's going to convert raster to vectors using this function called dot reduce to vectors. And inside the geometry, we're going to mention our study area, and the scale I'm going to mention is 30 meter, and the geometry type is polygon, and the label property is water, and the max pixel value is 1:10 power 10. And last, we're going to simplify the geometry to get a cleaner coastline. So to do that, we're going to mention the coastline. So the coastline is equals to coastline dot map function f, and return f dot set geometry, f dot geometry function dot simplify. The max error is 30, and set the year as so the unit is in years. And last, we're going to mention as return as a coastline. And the next step, we're going to create another variable called coast 2014 is equals to vectorized coastline, which represents the function we have created earlier here. So this is vectorize coastline. So this is the function we have created earlier here, and we're going to mention the water 2014. So here I'm going to mention the year as 2014. And similarly, we're going to define another variable called coast 2024 is equals to vectorized coastline of water 2024. So which represents this particular variable we have created earlier here. So you can able to see that. and we're going to mention the year. The unit is the year is 2024. And last, to add this layer, we're going to mention map.add layer, the coast 2014, and the color we're going to mention is blue, and the coastline we're going to output the layer as coastline 2014. And similarly, we're going to add another layer called map.add layer, coast 2024. Color we're going to mention in red, and we're going to output as coastline 2024. So previous is coastline 2014, and this is coastline 2024. So last is we're going to mention some visualization of change detection. So in order to see the accretion and erosion areas of this particular coast here using this particular technique. So first let us take a look at the coastline here. So we're going to navigate to the layer section, and I'm going to turn on the coastline 2014 and coastline 2024, and I'm going to turn off all of the layers. So this is the first layer, that is coastline 2014 here. So we're going to zoom in here. So now here you can clearly able to visualize the coastline of 2014 here. So you can able to see the distinction. So one side you can able to see that it extracted all the water areas, and also the boundary line here you can able to clearly visualize it. Similarly for the coastline 2024 here, I'm going to turn on this. So we're going to turn off the coastline 2014. So you can able to see the distinction here. So when the inland areas, it has picked up all the water body areas here, so you can able to see. But towards the coastline here, you can able to see the clear distinction here. So the line that separates the land versus water. So in the next step, we're going to visualize the change detection here. So to visualize the change detection, we're going to mention the variable called coastline change is equals to earthengine.image.cat water 24 and water 2014 and water 2024. And last we're going to mention the dot rename water 2014 and water 2024. And the expression I'm going to mention is dot expression is water 2024 minus of water 2014. So the water 2014 represents water 2014, and water dash 2024 represents the water 2024. So subtracting the so by water 24 subtracting water 2014, so it's going to give us the places of erosion and accretion. So you can able to, we're going to visualize it. So next step, we're going to add this layer, map.add layer, coastline change, and we're going to set the minimum -1 and the maximum +1. And the color palettes we're going to mention is red, white, and blue. So red basically is going to indicate the erosion eroded areas, and blue which is going to indicate the accreted areas, and the white which indicates the transition areas, and and we're going to output as a coastline change 2014 to 2024. And in the last step, we're going to export the coastline to our Google Drive. So first let us take a look at this image here. So we're going to navigate to the layer, and we're going to turn on the coastline change. So now we're going to zoom in towards the coastal part of this area. So you can able to see towards this is the coastal part of this area. Let me turn on this coastal 2014. So all the change detections are clearly highlighted here. So here, so red area which indicates the eroded areas, and blue areas which indicates. I'm going to turn to a satellite mode, and I'm going to adjust the transparency of this particular layer. So now here you can clearly able to visualize the result. So in this study region, all the red areas in the coastal part of the study region, which indicates the eroded areas, and blue areas which indicates the accreted areas. For example, you can able to see this part is got eroded and this part got deposited here. So basically this is the river mouth here. You can able to see the changes here. For example, all the red dots which indicates the erosions, the blue one which indicates the accretions, and you can able to see towards the coastal part here, and all the red areas which indicates the erosions here. Erosion is happening, and all the blue areas in the coastal part which can indicates the accretion. So then the last step, we're going to export the coastline to Google Drive. So to do that, I'm going to mention export.table.to drive. So we're going to mention the collection is coast 2014 and description is coastline 2014 vector. The folder is coastline analysis and the file format is shapefile. And last is we're going to export.table.to drive. So the collection we're going to mention is coast 2014-2024 and the description is coastline 2024 vector and the folder is coastline analysis and the file format is in the shapefile. So now to export this image, we're going to navigate to this option called task and make sure that you run your code, and in the task section we have this unsubmitted task called coastline 2014 vector and the coastline 2024 vector. So to export this vector to a Google Drive, I'm going to mention click this option called run and the window pop up saying initiate table export. To export this particular to your Google Drive, I'm going to click this option called run to export this shapefile, the coastline, to your Google Drive. So it will take some time to export this particular shapefile, and similarly I'm going to click this option and I'm going to run this, and it's going to export both the coastline 2014 and 2024 vector to my Google Drive. So now here you can able to see we have managed to export our coastline 2014 and 2024 to our Google Drive here. So it took less than a minute to export. So basically in this video I have shown you multi-year coastline extraction and change detection using Landsat 8 imagery in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like.